Good morning, good afternoon, everyone. My name is Min Sao Chan. I'm the Product Marketing Manager for MSC Apex, and today I'm glad to host our launch webinar for Harris Hawk. So I'm happy today to welcome Vijay Shankar, our MSC Apex Product Manager, as well as Larry Pierce, our Senior Lead Engineer at MSC Software. Today we're going to cover first the overview of the new capabilities in our latest release, and we're going to continue with the demo, and finally answer a couple of questions in our Q&A session. So feel free to type in the Q&A box.
Cool. Good morning. The message to you is that it can do more for you in this release. Let's take a quick look at the journey where we have come from. As you all know, we introduced in the early releases of Apex in the Arctic Wolf and Black modeling, which was predominantly targeted for CAD to mesh, and you all have seen how powerful it was and it is in creating the mid-surface modeling of most complex geometries, and also it is powered with what is called direct modeling with push-pull technology and edge and vertex track. And more importantly, it was always how easy it is to use and easy to learn. Subsequently, we started introducing the analysis capabilities in Apex. Today, to date, we can do linear statics, normal moves, linear dynamics, and linear buckling solutions inside Apex, and those were released in the subsequent Apex releases. And Apex will continue to be an open, integrated, and extensible platform for the CAE. And that's where we are heading, and that's where we will be. Where are we in our journey today? So today we will take a look at what is in Harris Hawk. And the one important thing what we're introducing in Hawk is composite modeling. In addition to that, we are making the enhancements and extensions to the simulation capabilities. And also, we started introducing what is called Apex to NASTAN interoperability. And that's what's been requested by most of you folks in the last couple of releases. And this is just the beginning in this release. And in the coming releases, you will have a lot more capabilities of Apex to NASTAN and NASTAN to Patran interoperability in Apex. So there's been a considerable enhancement in different parts of Apex, and there are enhancements in modeling, enhancement simulation, enhancements in the scripting capabilities, and all new interoperability in Apex. So what is the interoperability that we are supporting in Apex? Today, what you can do in Apex is to do the CAD to mesh and setting up the scenarios for conducting the linear static analysis, normal modes, and linear dynamics, in particular, the frequency response analysis and linear buckling. All these simulations are supported with the integrated solver inside Apex, and also you can explore the results within Apex. What is that we can do today in Hawk? Now you can export all these scenarios that you are setting up inside Apex as NASTAN PDF, so that you can take that one and run with the NASTAN externally, and also you can take that PDF into Patran if you choose to set up additional simulation techniques that is not today supported in Apex. So this makes Apex is more extendable and expandable to the NASTAN users and also as the Patran users. In the modeling area, as I mentioned, there is enhancements in composites, and there are enhancements in the beam modeling, and considerable improvements in the hex meshing, and also in the shell meshing. In shell meshing, in particular, we are introducing the what is called a washer treatment. And it's not that you can create washer only around a circular hole, as the case may be today, but in Hawk, you can do that one in the holes like elliptical hole or oblique hole or whatever. Plus, when the holes are close to each other, or when the holes are close to the boundary, and we are giving the treatment to the meshing so that it takes care of the quality of the mesh and it creates a good quality of elements around those holes and the washers and also close to the boundaries. Likewise, there are enhancements in the connections, in particular the tie connections. Since Apex is targeted for large fabricated structure simulation, and we are introducing the enhancements in the usability and what is called the topology visualizations. So what is the beam modeling enhancement? Up till today in Apex, you can define what is called a shape and a span concept, and in which you are able to define the shapes by defining the, for example, maybe a L shape or a T shape or different general cross-section behaviors that you can define in Apex, and you can calculate the properties and create the simulation models. But now we are supporting what is called a numerical shape. What does it mean? That means user today in Hawk should be able to define the beam properties by defining the areas I1 and I2, etc. It's a typical Nastran approach of defining creating the beams, and we are supporting that one in Hawk. And also we are making enhancements in the auto orientation and reversing the span. Up till now in Hawk, the beams orientation is tightly connected with the surface orientation. If you reverse the surface normal, it tends to reverse the beam orientation, and which is not desirable. And now in Hawk, we made it such that you can control the orientation of the beams by itself, so that you can orient the shape and also you can reverse the span. Additionally, you are able to export the C-beam and the P-beam properties out of Apex, and also you can import that one, the one that you create inside Apex. Hex meshing enhancements. Hex meshing is kind of unique in Apex. In FOSA, we introduced what is called splitting the solids, that is hex meshable. But we had a discontinuity in the mesh in the connected region, whereas in Grizzly, we introduced what is called a soft split, meaning the general solid body remains solid body, but however it's split into the regions that is hex meshable, which maintain the continuity of the mesh across the boundaries. Whereas in Hawk, we are making a lot more user-friendly and enhancements, such as if you define the washer around the hole and that is propagated through the solid, number one. Number two, you should be able to control the mesh fidelity in each cell by itself. You don't have to control the mesh for the entire solid. Number three, there is a control on the topology on the face. That means you have a better control on what kind of mesh fidelity that you would like to define on the face of the topology. Plus, whenever you select the multi-cells with a box pick to create the hex mesh, and there is internally a logic that is built in which order it has to create the mesh so that the mesh quality gets better. Number two, and also the failure rate is less. That means you have a better success rate of creating the complete mesh with the internal better logic. And more importantly, today in Hawk, you can also define different materials to a cell. So here is an example of a muffler system in which the tube is welded to the baffle wall, and the yellow region is represented by the weld, and the red and the green is a tube, where the green is the shell mesh and the red is the hex mesh. Likewise, purple is the hex mesh and the brown is the shell mesh, although it is a single body, and we use the split to create this region to be hex meshed. Now in Hawk, you have a continuity of the mesh between the red and the purple, and also the continuity of the mesh between the purple and the yellow and the red and the yellow. And now you can define the different material property for the weld representation, which makes it very unique. And these are the typical examples, and it is more applicable even in the gaskets and the seals, most of the time the rubber materials are made out of dual durameter materials. Those are the enhancements in the hex machine. And excuse me. What is in tie connection enhancements? Tie connection is unique to Apex, probably the unique to the industry. This is a technology we introduced to connect the parts together so that you can create what is called a monolithic model, yet maintaining the part and assembly organization structure. And by doing so, that the assembly structure in a CAE model exactly mimics the way that is done in the CAD world, and so that you can do the design change, the parts swap easily, unlike it is in the other systems today, where when you merge the parts, it becomes monolithic. In FOSA, we introduced tie connection. At that time, we could do only one tie at a time, whereas in Grizzly, we introduced where you can do the box pick, and it will create automatically all the ties within the box. In Hawk, we are making a lot more flexible, meaning now you can edit a lot of these ties or the geometry that's associated with the tie. For example, you can do the edge and vertex tag, or you can split a surface, or you can split a curve, or you can add a vertex, add or remove a vertex, or even you can defeature the geometry. All those things are possible today in the tie connected assembly model. This makes it a lot more user friendly, and usability of the assembly techniques will be much more enhanced in Hawk. And the linear static and the normal modes analysis were introduced in the early releases of Apex. In FOSA, we introduced the frequency response simulation, and in Grizzly, we introduced the linear buckling. In Hawk, what we are doing, in order to make the solution more expandable and more usable, now we are allowing you to create multiple load cases. And it can be done in both linear structures, linear static, and linear buckling simulation. And for the linear buckling, now you can also do with the pre-stiffened loads buckling characterization. And more importantly, once you define these scenarios in Apex, now you can export that one as NASTA and PDF. And this makes it a lot more usability of the product, not only within Apex that you can define the multiple load cases, but also you can export so that you can run that one outside of Apex in NASTA. And scripting. Scripting is open in Apex. Although it was released in the previous releases, but now in Apex, I call it as Limitless. The amount of scripting that you can do, it is limited to the imagination that you can do today. And we have expanded the macro record capabilities of scripting to the geometry, machine, familiarity, loads, boundary condition domains of the product. And now you can query, meaning you can introspect the geometry and the topology with the API enhancements. And there is a lot of richness to the APIs that is exposed in Hawk. In particular, you can do what is called a proximity search, or the search within the bounding box to find what's inside the bounding box, and you can introspect that one, and you can create whatever the things that you want inside that box. When I say whatever the things, meaning what exactly your intent of writing the scripts is made it possible with those APIs, openness, and richness. In the bottom right corner, what you are seeing here is an example where to create the spot welds, and the mesh is created in the areas of the spot weld, and this mesh is exported so that that can be consumed in doing the simulfrac welding. Whereas in the top right corner is a script that allows you to create a lot of connectors using the scripting capabilities. Now let's take a look at the example of a scripting. So here is the what is called the satellite dome, a most complex structure made out of maybe hundreds of thousands of parts, and they're all either bolt-ons or welded, and we need to see how the scripting helped today to create a model and assemble the model like this and ready to run the simulation. In this example, we are going to run maybe 4 different scripts. The step number 1 is basically to extract mid surface, assign thickness automatically, and auto extend all the faces with a new logic that is built in the Hawk and mesh that one. That is the script number 1. The second script is to create the fasteners in hundreds of locations in this model, and also to create the glue to glue the parts where it is not really bolted. And because in a typical model like this one, some part of the models are welded and many parts of the model are bolted, and we would like to see how the script will help you to create those things. And finally, to create the loads and boundary condition through macro record run the simulation. Let's take a look at the example of this one. Excuse me. So I'm going to import this the CAD model of the satellite dome and one of the 3 sections of the dome. And as you see here, and as you can see here, this assembly is made out of many parts, and these parts are bolted together, and many of these parts are welded together, and at the center there is a hub where all these panels are bolted together. Let's run a few scripts here and take a look at the power of the scripting, how it helped to create the meshed model, assembled model, and ready to run the simulation. Let's take a look at first macro. So the first macro in this case is created using the macro record. For one of the typical panels here, we run the macro to create the mid-surface, to assign the thickness, to extend all those parts, and create a congruent geometry, and mesh that one. And then that macro recorded script was edited to make it generic in nature so that that can be used not necessarily for the identical panel, but also for a similar panel, so that now that runs on a similar panel like this, or the flat panel, also on the web. At the center there is a hub, and now what you are seeing here, that recorded macro which is edited, and it is run through this model to create the mesh model. And you can see as quick as sweet it can be to create a mesh model like this one using the script. Okay. And so in this model, for example, between this side panel and these 2 flat panel, and this is the area where it is welded. And we are going to use the glue technology to connect those parts. And I'm going to run the macro to create the glue between those parts. And in this creation of the glue, although it is selecting the parts to be glued, but it is intelligently identifying the regions where it is to be glued. For example, if I select these 2 parts and these 2 parts, it could have welded along this flange, but we wanted to isolate only this area that is to be glued. And as you see here, all these center panels to the side panels, it is glued. Next, I'm going to run the third and the most interesting script here, which is to create the fasteners. And this macro, or the script, it is identifying all the bolt holes in this model. And then, with the vicinity search and the bounding box, it is finding all the parts that are close to each other, all the holes that are close to each other, aligned in a proper orientation, and then creating the fasteners at each of these bolt holes. And we created the flexible bolts in this case, and the bolt properties is automatically extracted based on the hole diameter. Now let's say you did a baseline analysis, and you could potentially can go and use your edge and vertex drag to modify the hole diameter, and thereby with the generative behavior, mesh gets updated, and simultaneously because of the hole diameter, the property of the bolt gets updated, and then now the new model is just about ready to run the simulation. So now basically with these three scripts, this model is meshed and assembled. I'm going to run one more small macro. Although it is small, basically this has a different materials, that is a database is created, and from that I'm going to assign one of the material. In this case I'm going to select a steel material, assign to the entire assembly. That is done. And lastly, I'm going to run one more script through which we are going to create the loads and boundary conditions applied to this model. Basically, there is a kind of the remote load applied onto the structure, maybe like a concentrated load, and an internal pressure load is applied on all the panels, and the bottom structure is kind of constrained, and as if it is connected to the rest of the structure in this case. So that is how the model is built using a couple of scripts. As you can see here, with the power of script, a structure like this kind of humongous one can be built, can be assembled. And now this is just about ready to run the simulation. I just ran the simulation just before the meeting. Here is the outcome of that simulation. And as I mentioned, that we do have set up the multiple events in this case, or multiple load cases. The first event is a load that is applied, kind of a remote static load on the structure. That's what you are seeing here. And now I can switch to the event 2, that is the pressure load applied onto the structure. And the event 3 is basically the combination of the two loads that's applied here. And so that you can take a look at the effect of the multiple loads acting simultaneously onto the structure, right? So this is again the one of the enhancements that is done in Hawk, so that we can define the multiple load cases and also look at the introspection of the results with respect to each of those different load cases. And even in post-processing, that there are considerable enhancements in the visualization. For example, let's say I'm interested in only looking at this part of the model, and I should be able to do like a query the model or select only the parts of interest. For example, I'm going to look at only those two parts, right? And if there is a area of interest, I can do that one. Like in the viewport, I should be able to hide, show only, like what you could do otherwise in the pre-processing area of the model. Now you should be able to take a look at the results and investigate that one only in the areas of interest. So all these things are the enhancement that is done, and by looking at all these things, it is making a lot more user-friendly, a lot more capable, and that's what we call we can do more with the Hawk. At this time, I would like to thank Larry, who provided the insight to all these scripts, and he created the scripts and helped us to build this model. And now it's just about the time I can turn it over to Larry, who can also take us further in helping us to understand the composites capability in Apex. So he's the subject matter expert in that area. Particularly, he also worked in the aero industry, and all of you know quite well. And I would request him to take us through the remaining power of Apex, particularly in the composites module. Larry, it's on you.
Hey, thank you, Vidya. Can you make me the presenter?
Yes.
Hey, great. I am the presenter. This is working out great. Oops. Don't want to do that. Sorry about that. minimize that. There we go. All right, so once again, my name is Larry Pierce, and with MSC Software, I'm excited to share with you about the new composite capabilities in the Harris Hawk release of Apex. And thank you for kind of hanging on while we were it's almost like the Olympics. We were fumbling the baton toss almost there. So anyway, I'm going to be demonstrating composite capabilities, and as I go through that demonstration, there's going to be a lot of things that you're going to want to take note of, but there's 4 things that I want you to particularly watch out for. And you may want to jot them down because there really might be a quiz at the end. And the first thing to watch out for is the data management capabilities that are related to composites in the Harris Hawk release of MSC Apex. We know that composite analysis requires the management of lots of data, the plies, the zones, the materials, the offsets. It's really a monumental task to manage this data so that your finite element model accurately reflects the physical structure. And I'm in a lot of devices, whether it's cars or planes that are made out of composites. I like it when the finite element model match the physical structure because I feel good about the results then. And we're going to see that the Apex efficiently and intuitively manages this data, such as the zones and the offsets, for you automatically. The key, and this is the thing to watch out for, is that Apex uses an intuitive manufacturing-based approach for defining the layup. This means that Apex is going to employ some of the concepts similar to what's on the shop floor, such as the tooling surface, sheets of material, flat pattern, ply schedule, and it means you're going to build your laminate kind of in that same way. First sheet, second sheet. The net result is going to be a finite element model representation that's closely akin to the actual physical structure, and the best part is that the data that you might have normally managed manually in the past, such as all the zones and the offsets, is managed for you automatically by Apex. Second thing to watch out for is verification and validation. Anytime you got this much data, it's going to be tedious to verify and validate the composite finite element model. And we're going to see that Apex offers both immediate and interactive feedback to make it easier for you to sleep well at night, because I don't know about you, but if I'm kind of wondering if my layup is what it's supposed to be, I might not sleep well at night. So Apex is going to help you get a good night's rest. Third thing to watch out for, we know that change is the only constant. Change in finite element analysis is often tedious, okay? Throw in composites, it's even more tedious potentially. And the beautiful thing is in Apex, change is automatic. It's going to be easy and intuitive to modify the layups. You'll see that. As you do this, Apex is going to automatically manage those pesky zones and the offsets for you. And you know, change is not just about the layup itself, but it could be model changes. Like you may find you need to remesh in an area to capture the results better, or there may be some geometry tweaks that are going to happen. Both of these changes are once again automatic in Apex because of Apex's generative capabilities. In a nutshell, what you're really going to see today is that in Apex, your layup information is mesh independent. And then the fourth thing to watch out for as we go into the demonstration portion is post-processing, because really it's all about the results, right? It's the results that you're going to use to make design decisions. We're going to see that Apex offers on-the-fly failure calculations, quick identification of the worst ply, and a bunch of other stuff, okay? So let's get started on the demonstration portion. And I've got here an airplane that I've made. This is not one you're going to want to fly in, okay? Nobody's going to be flying Larry's airplane here. But it is good for demonstration purposes. So let's get started. And the first thing I want to mention real quickly is because we have added the composite capabilities, we've added 2D orthotropic materials to Apex. This is a great opportunity to have a little quick script. I've got a great script I'll share with you to automatically populate your database with the materials automatically, okay? And let's now look at defining the layup. And I'm going to define the layup on this section of the outer skin. It's a section around a door and a couple of windows, and this is where we're going to define the composite layup. And we're going to do that in Apex through the attribution panel. You're going to attribute or add some information to our finite element model, and we're going to do that. We're going to attribute it with a composite panel. Now, the composite panel in Apex is a special object that's going to store a lot of information about your layup. It's the composite panel that's actually going to manage the zones for you, manage the offsets for you. It's going to manage the layup. And in particular, what we're going to learn is that this zone, this panel itself, is actually representing the tooling surface. That's how we're able to manage, especially the offsets, so easily and so automatically. So I have selected that geometric surface as my panel. This is going to be the tooling surface that I'm going to be working with. And in my example, this geometric surface, which is also the tooling surface, represents the outer mold line of the skin. Okay? A couple of things to notice about the panel real quick is we've got this arrow, or in engineering terminology, a vector, that's pointing outward. This represents our build direction. So we're actually going to be laying the plies opposite of this arrow, and the thickness will be building in the direction of the arrow. Since I'm assuming that my geometric surface represents the outer mold line, I'm going to flip this, okay? Because I'm actually going to lay my plies from the inside out, since this represents the outer mold line. If my geometric surface didn't actually represent the tooling surface, and I kind of wanted to be particular about my offsets, I can actually come in here and I can reset the panel to the proper offset position for the tooling surface. Now here I've done something that's very exaggerated so we can kind of visually see it, but you can also type in a number if you know what the offset is as well. I'm going to go back to 0 here because my geometric surface really does represent the outer mold line and where the tooling surface is. The second piece of information that our panel is managing for us is material orientation, okay? In particular, the material orientation of 0-degree ply on this particular panel, which is represented by the little red lines. So the warp is the red lines, the weft is the green lines. I can manipulate this with Euler angles, or I can just directly interact with this coordinate system. So I can come in and I can just orient it on the fly if I want to. I can type in a number if I want to. I know I get a lot of questions about orienting with respect to the geometry itself. So it's very easy to use this little coordinate system to select an edge on the geometry or some other feature of the geometry to orient with that. So I'm going to go back to the global X by orienting with an edge of the geometry. Okay, so let's go ahead and enter in an interlaminar bond stress for the Nastran central components. That's the SB parameter on the PComp card. And now let's start laying some plies. Let's look at what it's like to lay up a laminate using the composite panel in Apex. I'm going to turn my surface around because visually, remember, I'm laying them from the inside out, so I just kind of want to keep in sync with what's happening there. And let's start laying some plies. And before I start laying the plies, I want you to notice that when I selected this panel, that everything else went away in my model. And we call this the focus mode, okay? If you're laying up a panel, you probably want to focus on it. So rather than you having to manually hide a bunch of stuff, we do it for you. But you can quickly hit an icon to go back to the whole thing if you want to, or quickly hit an icon to come back. So this is called the focus mode. So let's lay our first ply. And I'm working like in inches and slinches for those that are maybe more familiar with metric units, and it's just a made-up model anyway. So the first ply is going to be a quasi-isotropic weave. So I'm just going to use a material orientation of 0, and I'm going to put it over the entire panel. Notice that I've got my material here, and I've also got my first zone, and that first zone just has that one ply in it. Let's do some additional plies. Let's put some plies around the windows and around the doors, okay? So we're going to come in and select some geometric surfaces around the door to put a ply around the door here. That's going to be a 45-degree ply. So I'm going to hit a middle mouse button here to kind of apply my ply. And we'll see that I've got a ply that's been added, and I've got another zone. And the zone kind of has a highlight around it to let me know something's happened. This is new and something's been added to it. So I'm getting a lot of visual verification. Even though I'm not manually creating my zones, Apex is letting me know what's happening. So if I see something that looks suspicious, I can dive in and take care of that. Let's make a panel around, add a 45 around this particular window. Let's add one around this window as well. Okay, and as I'm adding the plies, I'm getting more zones being created for me automatically. And at any time, I can just go in and click on a sheet or apply and look at what its coverage is, what its orientations are. I can also do the same thing for zones. I can, anytime I want to look at where a zone is located, notice how it highlights for me. Anytime I want to review what are the layers in that zone, I can do that at any time. So let's go ahead. We want to use our 45s in pairs. So let's do a -45. And let's put one around the door. Since I've already laid apply there, that's already a zone. I can just select a zone. That'll be a little quicker. So I'll put a -45 around the door. I'll put a -45 around this window. I know some of these I could combine, but I'm actually separating them out so I'll get a few additional zones to manage for me. And now let's add one more ply. And once again, I'm not advertising that you want to fly in my airplane. So we're going to add a 90-degree ply up here at the top, okay? So we'll add this ply up at the top, selecting those surface. And when I add that, once again, Apex is automatically making some additional zones for me. And once again, at any time, I can just review where these plies are, and I can review what the contents of the zones are if I need to. I'm going to do one more ply here, okay? That's kind of it's going to be the same quasi-isotropic as I laid down first. I'm going to lay it down last. I'm sort of going to bookend my laminate with this. I'm going to say I want a new ply with the same properties, and I'm just going to select this surface again. And this ply will be added to all the zones. That's why they all got highlighted. So once again, I'm getting great visual feedback to verify and validate what's happening as it's happening, okay? So we're going to let that be all the plies that we add for now. So I'll say done. Let's look at a few modifications that we might want to make. And maybe I actually want to come back to this ply, and maybe I want to modify its material orientation. Well, I can do that interactively if I like, if that's the way I want to work with it, or I can come back and I can just type in this data box if I want to as well. So I can actually manipulate the angles, the thicknesses, the materials. I can even change the coverage area, okay? So let's look at maybe this particular ply, and maybe I wanted it to extend a little bit further, okay? Maybe I kind of made a mistake when I was selecting the surfaces. So I can come back and I can actually increase the coverage area of that ply. I'll select the additional surface, middle mouse button to accept it, and once again, Apex has found that it needed to add a zone for me automatically and modify a zone for me automatically. So there's several things that I can do here. I can modify orientation, thicknesses, materials, coverage areas, and I'm getting a lot of feedback, once again, and a lot of things that I can quickly visually verify to make sure that I've done exactly what I think I wanted to do in the first place. So I have purposefully not meshed anything yet because I kind of wanted to emphasize that this is really mesh independent. But I'm going to go ahead and mesh it now because now a lot of the change that occurs is based on the mesh itself. So let's go ahead and define a surface mesh, okay? And let's actually change the color of that so it'll show up just a little bit better. We'll pick a little darker color. And here I've actually got a mesh, and let's look at some changes to the mesh and the geometry and see how they affect our laminate layup, or if they affect the laminate layup at all. And I want to introduce us to what we call the core sample tool. You know, you can imagine in a larger finite element model, like for this entire airplane here, I might have a lot of composite panels, and I may not know which panel to go to modify what I'm looking at. And the core sample tool lets us just mouse over regions of the model, and it just quickly gives us feedback as to how many plies are there, what the plies are, what the orientation is, what the relative thickness is. In particular, I can actually plant at any particular location. So I'll plant the core sample tool, and then I can quickly just review what are the layers, and I actually see, you know, what the individual plies are, not only in my area that I've sampled, but if they extend beyond that, I get that feedback as well. And if this is an area that I need to modify, I just double click and it just automatically takes me right back to the panel tool so that now I can actually start making some modifications to the layup in this particular panel. Okay? Let's go back to the core sample tool, and I want us to note this area here that only has the 2 plies on it. Okay? And let's make some changes that will affect that area. So the first change we're going to make is we're going to split the surface. All right, maybe I need to split the surface because I need to do some manipulation of the mesh in order to better capture some results. As a matter of fact, maybe one of the changes that I might make is a change to a mesh seed, okay, a change to a mesh seed. And let's go back to the core sample tool, and what I see here is, you know, I still got that zone, I still got those two layers, okay, so I made a change to the model, to the mesh, I actually changed the geometry, I split a surface, and Apex is managing the zones and the layup for me. I can even come in and say suppress that curve that I just created, so we'll suppress it so the mesher doesn't see it anymore. We'll go back to the core sample tool, we still got two plies, okay, so once again, Apex is managing my zones, managing offsets, all that information automatically for me, okay? So that was a mesh-based or a geometry change that was kind of dictated by the mesh. We saw previously that I extended ply coverage by selecting some additional area, but maybe I'm going to extend the ply coverage by actually changing the geometry. Maybe I'll look at the zone that's in sort of a grayish color here that's around the door, and I realize I want to make this bigger. So I'll just leverage the direct modeling, the vertex edge drag capabilities that are in Apex, and I could do something that was more exact, but for demonstration purposes, I'm just kind of, you know, arbitrarily eyeballing it here so I can expand that zone because maybe there was a need for that zone to be larger. I can see that I have kept the same zone identity because it's the same color here, all right? Let's make another change, all right? Let's actually go in and add a doubler around the door. Okay, I fly a lot of planes. When I see the doubler, I know somebody's done some analysis. That always makes me feel good. All right, so we'll do a split, just sort of an arbitrarily shaped doubler here, and there we go. Just sort of an arbitrarily shaped doubler that I'm going to add some additional material to. So I can come in and I can use the core sample tool. I can quickly see that, you know, I've got the same zone even though I've split that surface. Let's plan it here. And we're planning it here so that we can quickly go to the panel that defines that zone, okay? And once I'm here, then I can come in and I can add another ply. Let's make it really thick, okay? And let's just make it a 45-degree ply. And let's apply it to the surface that represents my doubler surface, all right? So we'll see that we get a new zone, okay? And we should get a new zone. You might be curious as what the relative thicknesses are, so we can actually use the thickness tool, and I can see that that's absolutely thicker because I specifically made that ply thicker so that it would highlight. We can also see that I'm building my thickness of my laminate inward here toward the inside, and that's exactly what I thought I was doing as well. So let's do one more ply, okay? One of the things that always happens to me is I just make a lot of mistakes, to be honest with you, and so change doesn't get me, I get myself. And so maybe I misinterpreted the ply schedule. There's really supposed to be two of these quasi-isotropic plies at the very beginning. I could easily just come in and just make this thicker, okay, that would take care of it, but then my ply schedule and the number of plies in my finite element model would not be the same, and that might confuse people later on down the line. So I'm actually going to add an additional ply with the same properties. I'm going to apply it to the entire panel, okay? And the thing that I noticed, remember we're kind of using a manufacturing-based approach, is that this ply is actually last. I wanted this ply to be underneath ply A here, okay? It's been added to all the zones. It's very easy to reposition it. I'll just come in here to any particular zone that contains this ply, and I'll just reposition it. Notice how it's going up. Notice how I'm getting feedback that I'm modifying a lot of zones at this case because this ply is actually in every zone, so I expect to see a lot of modification. And I just keep moving it until now it is in its proper position. So hopefully you see that whether the change is to the layup itself or the mesh or the geometry, that all of its composite capabilities in Apex are generative. Let's do an analysis real quick so we can actually do some post-processing. So I'm going to place this in the analysis window, and I'm going to modify my scenario so that I can add strain. I know a lot of people look at strains when they're looking and evaluating failure of their composite, and we will run it. I don't have any stringers. I don't have any frames. The results are very made up, but they're also useful for us to kind of get a feel for what the capabilities are in Apex when it comes to looking at the composite results. Okay, so the deformation is definitely kind of weird because we don't have the backup thickness that might be there. Let's change the color, look at a little lighter color, and let's also add, I like to look at the element edges. All right, so there's going to be my model. And let's look at the results that we might look at for a composite model. Okay, so we will look at some stresses first. Okay, and let's look at sigma x. Okay, and I know that I'm looking at sigma x because I can go to the system and I see that I'm looking at the ply in the ply material orientation versus material, which would be the material axes for the panel itself. Okay, I can look at results for the individual zone layers, or I can also look at the results for the individual sheets or the individual plies. If I need to remind myself of what the material orientations are, I can quickly do that as well. So, you know, I don't have to go very far to actually see what the material orientation for this ply is. I can also come in and select maybe all of the plies, okay, and I'm looking at sigma x, which would be the fiber stress here, and we'll turn on some hot spots, okay? So I see what the worst sigma x or the fiber stresses are, which ply, which locations in this particular case, all right? I can also look at individual components, you know, warp and weft and a bunch of other components. I can also look at strain if I want to, okay? Once again, I can look at this on a ply by ply or layer by layer basis if I want to, okay? Or I can look across all of them if I want to quickly identify. Let's look at sigma x. I'm at the strain in the x. I can look across all if I want to quickly identify worst ply and worst location. In addition to looking at the stresses and the strains, I can look at the interlaminar shear stress, okay? Looking at the interlaminar shear stress, this is just going to be in the material system of the panel itself, okay? So I can look at that. I can also look at composite failure. And when I look at composite failure, these are on-the-fly calculations, and let's actually look across all the sheets that we have. These are on-the-fly calculations, and I have a choice between such as Hill or Hoffman, Saiwu. I can, of course, do max strain if I want to, and I can, of course, do shear stresses, transfer shear stresses as well. So I'm running short of time. We want to save time for questions, so I have one more thing I want to do real quick, all right? I want to export this because one of the things Vidya said is we export run-ready bulk data decks. So I am going to export from the scenario, and let's put this on my desktop so I can find it. So we'll save that, and I apologize to my friends in Europe. I am going to use inches and slinches, and so we've exported our bulk data deck. And I've actually got Patran going, so let's read it in real quick. That'll help us to kind of verify that what we've got going here is what we thought we had going. So let's go and import. Let's import the Nastran input file that I just wrote up. It is on my desktop. So this is importing that. And let's go in and let's actually create some groups. So we'll create groups based on our property sets, okay? Have a bunch of those. Let's post them, unpost, and color. And what we'll see here is we'll see colors in the model where the zones were. So I can see all of my zones that I had. So we've exported the PCompGs. We've got all that information ready if you wanted to do something else with this model, especially if you wanted to run it in Nastran, okay? So let me go back to presentation, one more slide, and then we're going to be wrapping it up. A couple of usability enhancements, or several usability enhancements, went into the Harris Hawk release of Apex. A big one is the enhancements to the topology display of your finite element model. For some time now, we've been able to color code the topology, like red for free edges, yellow for non-manifold, green for like feature edges, but we were not including the effects of the edge ties. We were not including the effects of the glue. So things like glued connections and edge-tied connections would show up as red as if it were free, which it's really not. It's really connected. So we've greatly enhanced the topology display to consider additional connections other than just a congruent finite element model. We've also made some improvements to the transform manipulator. The transform manipulator in Apex is very powerful in terms of translating and rotating. It has always sort of depended on that you might know what's next. Okay, there was some help for that, but a lot of people kind of struggle to see what to do next. So we've actually added some additional dialogue here to help you know what to do next, and I think you're going to find that you're really going to be able to leverage the transform manipulator much, much more in the work that you do in Apex. NVIDIA has already illustrated. We made quite a few interaction improvements in post-processing, making sure that you can show and hide the model just like you can in the modeling aspects of Apex, and also made it easier to identify the target for the plot. With that, I'm going to turn back over to Vidya, and he's going to wrap it up for us. Thank you.
Hey, thanks, Larry. Thanks for your deep insight to the composite modeling. Can you hear me?
I can hear you.
Thanks. Just want to make sure. All right. So in Hawk, as you could see, that we have done quite a bit of enhancements, in particular, all new composites modeling and all new interop capabilities, and more exposure to the scripting capabilities, and continued enhancements in hex meshing, and continued enhancements in the tie connections. With all these new capabilities and exporting the models from the scenarios so that you can run even the NASTAN outside, I believe, and we believe, now Apex Hawk is more open and more extended and more capable. You can do it much faster than before and more reliably because we have a lot of visual capabilities to figure out, is it right, is it done right, is it done correct or whatnot. And scripting, as I mentioned, is limitless to your imagination what you can do.
That being said, thank you very much all for attending the webinar, and stay tuned when the release is out. Thank you very much, Larry. Thank you very much, Vidya. Have a good day.
Thank you.